are recording right now. And so welcome, week 8, officially now, no matter what day you consider to be the halfway point, we're past it in this semester. And today we're starting some new material. There's two good things I've always thought about physics. One of them is you don't memorize a lot. A lot of other disciplines, maybe your major, you have to memorize a lot of facts in order to be participative in the discipline. I think of my high school biology, and I was just terrible at memorizing all those species and whatever having to do with various plants and animals, and I was just no good at that. In physics, you don't memorize much. In fact, things like the acceleration due to gravity near the surface of the Earth, 9.8 meters per second squared. I suspect a lot of you know that number right now, even though you never sat down intentionally to memorize it. You just used it 4 or 5 times and the number may have stuck with it, just about 10 meters per second squared. You do have to memorize things like units. That is one of the things in physics we insist you memorize. But the equations we give to you. You just have to know what the terms in the equation are. What do the symbols stand for and what do they mean? So that's the first thing. The second thing about physics that I've always thought was great is it self-reviews. Because today we're going to start talking about rotational motion. We've been talking about circular motion. It's just kind of an added angle to something we've been thinking about, things going around in a circle. But now we're going to start talking about rigid objects going in a circle. And we're going to review some of the kinematics we did back in chapters 2 and 3. Okay, kinematics, of course, is the study of motion. When somebody says kinematics, you think about positions, displacements, velocities, and accelerations. That's what the study of kinematics is all about, calculating and using those things. And so as you saw in the reading and the pre-lecture video last night, what we're going to be talking about now is rotational displacements, angular velocities, angular accelerations, and then the thing that causes an angular acceleration, a torque. Directly analogous to positional displacements, just linear velocities, linear accelerations and forces. And so hopefully the parallels between the two different types of problems, different types of motion will be stark enough that it forces you to go back and go, oh yeah, I remember that. We're reviewing that right now. It's actually in some ways reviewing for past material, reviewing of past material. So the first thing I want to do is just quickly share a screen with you by PowerPoint. And we'll do a couple polling questions here. But just before we get started, remind everybody, since it is new material, what the equations are. Back up one. And saw this in the video last night. There's 3 equations that relate the old linear quantities that we talked about, displacement. Sometimes we call displacement a delta x. Other times we might have called it like a d if it wasn't along a principal axis. And so there is a relationship between an angle, delta theta, shown up in the diagram there, okay, and the radius of the object and that distance d, which you can see is drawn as an orange arc out on the circle. That formula has actually got a name. Mathematicians have given it, called the arc length formula. Okay, and the arc length formula is just that d is equal to r times theta. All right, that I want to make a point. If you missed it on the video or the reading last night, what are the units then of theta or delta theta, a displacement in theta, a change in theta? And the answer is d is in meters, r is in meters, it's meters over meters. They cancel. In point of fact, radians are really just a placeholder unit because it is a non-unit. But we want something there to remind us that we just divided the meters away in the 2 lengths, the distance on the arc and the radius. Any questions about that? Should open up the chat just to see if anybody's got something. All right, there you go. So the next thing then is you just divide that equation by a time interval. And you take a displacement, you divide it by a time interval, you get a velocity. You take an angular displacement, divide it by a time interval, you get an angular velocity. And yes, that letter that looks like a W is the lowercase Greek omega, the last letter of the Greek alphabet, it's lowercase. And then if you divide the second equation, the green velocity, by a time interval, and you let the velocity change, of course, you get an acceleration. We refer to that as a tangential acceleration to distinguish it from a centripetal acceleration. Okay, so don't confuse the two. We'll put R or C when we mean that acceleration that changes the direction of the velocity. This is the one that's changing its magnitude, making it increase or decrease. And of course, divide omega by a time interval, a change in omega divided by a time interval, and you get an angular acceleration. So those three equations are what translates, if you will, between linear velocities and accelerations and distances and angular velocities and accelerations and angular displacements, theta, delta theta. Okay, the next set of equations you have to see is our rotational motion equations in the red box there. And, the analogy to linear motion is hopefully apparent. You just take what used to be an X or perhaps a Y if you're working the problem vertically, and you substitute every X, you substitute a theta, the subscripts stay the same, and every V you substitute an omega, an angular velocity. Okay, and every A you substitute an alpha, an angular acceleration. And otherwise the equations are identical. And so if you were good using them back in chapters 2 and 3 in the first midterm and all those sorts of things, no problem here. Just, you don't have to memorize them, look them up. I put them on the worksheet for today. These equations are both, all the equations we've talked about are there. Constant angular acceleration is a category of motion that we're going to study. Any questions before I go on to polling? All right, well, good. Then we'll move on and I'll open up the polls. Almost like an election day, right? So I guess the good news is while the material is new, it's not radically different from what we've been doing all along. There's a consistency to physics. All right, hopefully you're seeing the poll here and the first question, and hopefully they even match. Okay, and so we're looking at what is an angular displacement, and hopefully you're familiar with an analog clock. And an analog clock, the hour hand moves around 12 hours, right? The analog clock, the hour hand goes around twice a day. And so what's the displacement during a 3-hour interval? I do worry about this question because more and more people have digital watches. Fewer and fewer people have seen and worked with analog clocks. Someday this will be an obsolete question, I think. And I recognize you may be able to answer the question had I given the units of degrees, but you do need in rotational motion to get in the habit of using radians. Physicists work with angular motion typically in radians. All right, looks like just a couple more people to enter in. We're a little over a minute. Give you just a few more seconds. All right, maybe there's some people on their phone or something, so I'm going to call it here, end the poll, and share the results with you. And I think most people are saying pi over 2 radians, which I think I can live with, because for me, there's noon, right? 3 hours later, our hand is over there. The angle, if I'd asked it in 90 degrees, I wonder if I'd have changed the results, but 90 degrees corresponds to pi over 2 radians. So the nine of you that pick that, you're good to go. I'm not sure why. I wonder, did a lot of people pick B because they thought 90 degrees was pi over 4 radians, or did they pick B because you thought the hour hand went around 24 hours for a full cycle, and 3 hours was, I guess, not a quarter, but an eighth of that, and that's why you went to pi over 4. But just as a check, if you were able, if it was the first one, 90 degrees, right? If you're converting to radians, the easiest way is to think about a full circle is 360 degrees, and that's equivalent to 2 pi. Other people like pi over 180, if you will. But if you do that, you can see 180 over 360, that's a half of a pi. Okay, and so that's the equivalent of 90 degrees. So those, the majority of you, the 9 who picked C, you got it. If you pick B, you're on the, I think you're on the right track. I wonder if it was the conversion issue or just being able to visualize 90-degree rotation of the hour hand on a clock. But that's it. All right, we'll stop sharing that. We'll move on to the next one. And always got to scroll to the bottom here and launch the poll. Object rotates, and so right here I might write omega as that to represent that. And it's moving it with a constant angular speed. What's its angular acceleration? I suppose the good news is if you'd have gotten this problem right for linear velocities and accelerations, you'll still get it right here for angular velocities and accelerations. If you were going to get the problem wrong for linear velocities and accelerations, well, you'll still get the question wrong here, I guess. A couple more people in. Got 20 have voted so far. Somewhat shocked by this, I think. And you're all making me feel like a failure here this morning, but that's okay. I can live with it. I'm going to end the poll. So I don't have to look at it any longer. And, you know, I'm not even sure, truthfully, what equation B is. It's not one that's in my my repertoire of memorized equations. V squared over R clearly is centripetal acceleration. But here's the point. Either an acceleration back from chapters 2 and 3 was a change in velocity over a change in time. And now angular acceleration is a change in angular velocity over a change in time. Okay. And if it says constant angular speed, that means this right here isn't changing. A constant angular speed means there is no delta omega, just like a constant linear speed would mean there is no change in velocity. Well, if either of those two are zero, their counterparts, the acceleration, regardless of what time it takes, okay, is also zero. And so the answer is C there, zero. And so again, the 9 people who got that, I have no idea even truthfully what this equation is. It's just a distractor that was put in by the guy who wrote the question, a guy from Harvard, Eric Mazur, wrote this question. And I don't know what that's supposed to represent. So I'm kind of surprised a lot of people jumped on it. But I'll stop sharing here. We'll move on to the next one. And now we have a ladybug and I guess a gentleman bug, just because we needed 2 there. One revolution per second is the angular speed. And I guess the ladybug is the outer edge. So this is the lady right here. And this is the gentleman bug, the other bug. He's about halfway, it looks like. All right, you're making me feel better here now in this one. Good, good, good. 22 at 27, we'll give a couple more seconds here. 24, that may be everybody because other people may not have 25. Looks like we can get 25. All right, I'm ending it and we'll share the results. And whew, I was worried there. Okay, yeah, the good news about rotational motion is we say we're talking about rigid objects. So every point on that disk is rotating with the same angular velocity, 1 revolutions per second. That's the definition of rigid rotational motion. Okay, if somehow that thing was plastic or something, and the outer edge could move out and twist faster than the inner edge, well, maybe, or the inner parts, well, then that wouldn't be true. But that's not what we're going to be studying in PHY 101. That's a very advanced problem, not going to be something we'll ever worry about. So all points move with the same angular velocity. Okay, and that's good. You all got it. Move on to the next one. I got two more that I'm going to do a problem, and then you're going to do a bunch of problems. All right. Launch poll here. All right, so we threw a coordinate system out there at the end and put it right on top of the ladybug. And the ladybug's on a spinning disk. And we want to know what's the direction of the centripetal or radial component of the bug's acceleration. And this isn't any different from what we did in the last two chapters on circular motion. Two chapters, one chapter. Quickly, I forget. Yeah, both chapter 6 and chapter 7. We defined radial or centripetal acceleration in the same direction here. And so nothing new. That's the good news, I guess. All right, majority of people are doing it. We'll end right here, and I'll share the results with you. And I'm happy again because apparently I'm doing a better job here now. The majority of people see it. Remember, if this bug is going to move in a circle, okay, that must mean there is a centripetal acceleration pointed that way, okay? And that centripetal acceleration is in the negative x direction on this coordinate system, okay, right along there. Question I would ask is kind of a review question from chapters. Let's see, we're in 8 right now, right? No, we're in 7 right now. So 5 and 6. What force is causing that centripetal acceleration? So that's a key point here. Newton's second law: force causes an acceleration. What is causing this centripetal acceleration? Just think about it for a second. And I guess if you didn't have this force, the ladybug would just kind of, once you get started, move straight off, right? We had that question before. What would happen if this force all of a sudden went away? And the answer should be the friction force between the feet and the disc. If that wasn't there, the ladybug would just be thrown off the turntable, thrown off the disc in a straight line. So friction causes the centripetal acceleration here, which is always towards the axis, towards the center of the circle. All right, good. Move on to the next one. Stop sharing that. Move to the next problem. I think this is, now what number am I? Did I get off kilter? Yeah, I guess this is my last one. And then I have a problem to do. That's why I have one more slide. So we'll launch this. And now the initial speed you can see is this way. And so that means the ladybug is going that way, right? But slowing down. That should be a V right there. I don't know why I was thinking of the acceleration you have to answer. But she's slowing down now. So what direction is the tangential acceleration? Good. I think a lot of you have it. You see it. All right, 22 people in, almost up at a minute here. All right, got 25. I'll take 25 at 27 this morning. On a Monday, that's as good as it gets. Sometimes I'll share the results with you. And I agree with the 14 of you who said negative y direction, right? Because if it's slowing down, okay, that means right here, If the velocity is going, I guess, counterclockwise and slowing down, that would be an acceleration in the opposite direction. That's what we said decelerations are. When something's moving one way and the acceleration is in the opposite direction, that means it's slowing down. And so that is what we want. And we subscript that with a T. Notice the acceleration is sort of tangent to the rim, okay, as opposed to the radial or centripetal, which is always pointed towards the center. So an object can have two components to their acceleration, and that's the point here. If the speed is changing, if the angular speed is changing, it has a tangential acceleration. Something going around in a circle always has a centripetal acceleration. All right, stop sharing that. I want to do a problem. First time going through a set of material here, I guess. Did I share the results with you? See that if you're in the 14, you got it right with the minus y. So good work there. Stop sharing, and I'll put that away. I want to do this problem real quick. New material, so it's good to go through with me one time. I did do, if this one problem doesn't cut it, I obviously did do another. I think I did two last night in the pre-lecture video of this same type, but I just want to make sure everybody sees this, and some of the words are important here. And so what are we given? It's one of those old-fashioned vinyl record players that maybe your parent has. I got mine. Mine was not working this summer, so I had to buy a band. It had stretched out over the 20 or 30 years. I don't use it that often. And there was a company that sold a new kind of big rubber band that helped turn the turntable. And so I can play my old records from college again. There's just something pure about that as compared to a CD or some kind of digital format. In any event, the record players back in those days, the big records spun at 33 and a third revolutions per minute. Remember that word per, that P right there just means divide. So this is a revolution. And the problem is, of course, radians start with R as well. So you got to write a couple more letters per minute. Okay, that's what that means. And the question is, how far does the record player go in 2 seconds? And then we shut off the record player motor and it spins down in 20 seconds. I want to know what's the angular acceleration. I'm going to figure out, I think, what this, yeah, and now I don't have to do a speed. I'll just figure out how far the record player turns until it comes down to a stop, okay, till it coasts down to being at rest. So it's really two problems. And you may be looking, okay, what symbols do I use here? Okay, and I would use F for the given information. I think the frequency, because we said F is either in cycles or revolutions per time, okay, that's what I would label the 33 and a third, okay, and I will write revolutions per second, okay, and then I have to convert that. Oh, it's not per second, is it? Nobody jumped in chat to correct me there. That's where I want to get to. It's given as revolutions per minute, right? So I need to get it to revolutions per second. And the way I'll do that is I'll multiply by a conversion factor that 1 minute is the same as 60 seconds. And the minutes cancel. And I got revolutions per second here. That's what I want. And 33 and a third, 33.33333 repeating divided by 60. You can see it's just a little over a half. It turns out to be 0.555, and that 5's repeating. So the last one, wherever you stop, I guess you got to round it up to 6. And that now is revolutions per second. Okay, well, we also talked about angular velocity. That's the Greek omega. And there is an equation that relates the two. Okay, it is 2 pi times the frequency. And while that is an equation, if you think about it, all the 2 pi here does is it converts revolutions to radians, doesn't it? Because there's 2 pi radians in every revolution. And so that 2 pi is just a conversion factor built into an equation. Kind of cool. You can look it up. It's on your equation sheet. But if you don't want to, you don't have to. Just remember that there's 2 pi radians in a revolution, and you're going to convert 0.556 revolutions per second to radians per second, because that is the unit of the angular velocity or the angular speed. Okay, so I go 2 pi, about 6, right? 3.14159 times 2, a little over 6. That's what the factor is, times 0.556 revolutions per second. And what I get here is 3.49, about half a six. 3.49 radians. And I can see why I just can't write R, right? I got to go radians per second here for omega. Okay, hopefully everybody's good with taking the given information then. And then the first thing I want to know is, well, how far does it go in 2 seconds? How far does it rotate? What's the angle? And so one of those kinematics equations, not that one. Come on, it's my handwriting here. We said for constant angular velocity, omega final is equal to omega initial. I'm sorry, theta final is equal to theta initial. The final angle is equal to the initial angle, plus what I need to do here, omega times the time interval. And that's the initial omega. It's the same omega anytime here, times the time interval. Well, we'll start from zero angle, right? And we want to know what the final value is. So all we do is we take 3.49 radians per second, and we multiply by that 2 second time interval. The seconds cancel, and I have a number of radians, about 6.97. And I always urge you to think about how, that's a 9.7 radians. I always urge you to think about, well, what does that mean? Okay. And remember, we said 2 pi is about 6.28. So it's past one full revolution. That's how far it goes in 2 seconds. Okay. Any questions on that? All right, one more then. I'll keep pushing. And I gave myself a little bit of room here. Let me just clear that. Format it. I want just completely clear. Yeah, that's fine then. It's insisting to give me a title here. All right, so what did we leave off? We had a speed, an initial speed of 3.49 radians per second, right? So that's the initial speed, 0.49 radians per second, okay? And I guess we're told that it coasts down to rest. And look at that, PowerPoint's giving me design ideas. Thank you. It coasts down to rest. So I guess that means the final, oh, you turned that off on me, huh? The final velocity when it comes to rest, we can do this. Come on, tool. Draw. Then try that color. All right, the red pen doesn't seem to be working. It's probably a little obnoxious anyway. Final is equal to 0 radians per second, comes to rest. That's what rest means. Just like it did for linear velocity, rest is 0. And so I want the angular acceleration. The equation is that the final angular speed is equal to the initial angular speed plus the acceleration times the time interval. Well, we said the time interval was 20 seconds. And so I can solve for this. 0 is equal to the initial 3.49 radians per second. And I'm going to get sloppy here because I'm in a little bit of a hurry, I guess. Plus, and I just have to remember, I don't mean revolutions anymore, plus the angular acceleration times the time interval, which we're given in the problem. Okay, hopefully pretty straightforward then. The first thing I can see is if these two things have to add up to 0, that angular acceleration is going to be negative. This thing is slowing down. And so angular acceleration is minus 3.49 radians per second divided by 20 seconds, which would be equal to minus 0.174, minus 0.174. And that's, look at the units now, not meters per second squared, but radians per second squared. Okay. And then the last question is, well, how far in angle does it turn while slowing down like this from an initial speed of 3.49 radians per second to a final speed of 0? And hopefully you'll recognize there's an equation theta final, the final angle, is equal to the initial angle plus the initial angular velocity times the time interval plus, don't forget this 1/2. People used to do that in constant acceleration problems as well. 1/2 the angular acceleration times the time interval squared. Don't forget to square because you got it squared right there. It has to cancel. And so we'll start from an initial angle of 0 again, because why not? We're trying to figure out what the final angle is right now where it's at 0. And so I guess I'll put all this stuff in. I'll go 3.49, the initial speed, radians per second. The time interval to coast down, 20 seconds. Okay, and then plus 1/2. Now be careful here. We just decided this was a negative angular acceleration, so minus 0.174 radians per second squared times the 20 seconds. I'll just be able to fit this in here, but that's got to be squared. Okay, and let's see. Second cancels second, so I'm left with radians, which is what I want. I want an angle in radians. And second squared cancels second squared. And again, I'm left with radians, but this is negative, okay? When I put this into my calculator, I get, remembering this is negative right here, I get 34.9 radians. And so that's my answer, okay? That's my answer. And the question you might always think about is, well, how many times around, how many revolutions does it spin? Remembering that there's 2 pi radians in every revolution. That's about 5.5 turns. It'll revolve around about 5.5 times as it's coasting to rest. And so that's a logical thing. Okay. I don't think anybody's seen a turntable come to a stop almost instantly. And I don't think you'd expect 200 turns as it comes to rest. So that's a reasonable number. We're fine leaving it as just about 35 radians is what it turns. Any questions on that? All right, then you're ready to go. All right, so the worksheet for today, I'll stop sharing this with you. Unfortunately, you just have to do all the problems here. Okay, and that's sort of the way it goes. I've given you some speeds, frequencies, Fs, just like I did. You've got to convert them to omegas. You got to convert them to linear speeds, okay, at various points on the object. You have to find an angular acceleration, a tangential acceleration, even a centripetal acceleration. And then just like I did, I forget if it's slowing down or speeding up, but using some of the kinematics equations to figure it out. So there's 8 questions. They're all pretty quick, but everybody has to do each and every one this time. Here are your equations, because it is day 1 and there's no reason to memorize them. And that's about all I got. So I'm going to break us up here into, you've got 20 minutes now to work on this. I'm going to jump around from group to group. We'll go to let's go today. How many people we have? We have 27. That's a good number. We'll create 9 breakout rooms of 3 each and work on these problems. When we come back in about 15 minutes or so, I'll give you the numbers just so that you can check to make sure you got it. But then everybody has to turn in by Wednesday all 8 of the problems. Any questions? Off to the breakout rooms to work.